Greetings, guys, and today we are going to make more modules for our pipeline BatPu2. So, in the previous episode, we have finished the fetch stage and the instruction ROM and the ADU. Now we have to make other modules for our stages. Something that I forgot to include was the call stack. So that's the first thing we are going to design. Create a new file and call it callstack.sv. So our inputs are going to be clock enable and execute mode. So let's see. Now another input we need is the program counter. And then our output is going to be data out. So let's see. We need to create our memory first. So we are going to keep this original. Mattbatwing's call stack on Minecraft has a depth of 16 stages. So we are going to use 16 stages. No, wait. This is the bit width. Now 16 stages here. Now the register we have to make is our stack pointer. So to keep this basic, the stack is going to grow upwards. So let's see. Make an always fflog. So in our vlog, if clock enable, then pointer is updated. No, wait. If execute, then okay, we can simplify this by using if clock enable and execute again. Pointer is set to mode multiplexed with pointer plus mode. We are going to multiplex this -1 and 1. So if mode is active, the pointer will decrement, else it will increment, pushing and popping from the stack Then for our call stack, it's going to be indexed by our pointer. Input is going to be data in. Now we end our block. And we assign data out. So let's check for problems. Can't find definition of variable data in. Oh yeah, because we just changed the name here. Can't find definition of variable call stack. Oh, here. Fixed. And our errors have been fixed, so we got our call stack. So we have an important choice to make. Number one, use forwarding for the flags so we can jump or branch from the decall stage. Or two, jumping. No, we should use bubbles. We are not going to use branch prediction at the end. So let's start making our decode stage. Before that, let's done. So we got instruction RAM, call stack, LU, and decode stage. I mean fetch stage. Because we are right now making a decode stage. So in our decode stage, we are going to fetch the registers. And then the data is going to be transferred to the execute stage. So let's see. For our inputs, we first have clock enable, invalidate. This one is important. When the decode stage is invalidated, all the control lines are set to 0, basically a no op, to prevent they usually in this case for preventing issues with branching and jumping. Other input we have is register write enable. Now have to make another input for our writing address of the registers, an input for the writing data, then for the outputs, and inputs are instruction bus. Then for the outputs we have source 1, source 2 from the registers. As I said previously, I don't like calling them A and B. I'm more formal with this kind of things. I prefer calling them source 1 and source 2 and destination, not A, B, and C. So let's see. Source 1, source 2. Then We also have to output. See here. We have to input and output the control lines too. I'll be right back in a second. I'm back, so we have to input all the 18 lines. No wait, that's for the execute stage. We have to output 18 lines here. So for now these are our inputs. Let's see. We have to instantiate our modules. First, the register file. So for clock, write enable and clock enable, these ones are easy. Now we have to see data in. Then for the addresses, we only have address 1 address here. We only have to grab from the instruction bus. So let's check our instruction set table. Let's see. Reg A 8, bits 8, 9, 10, 11. 11 down to 8. Then for the RS2 address, have inst bus 7 down to 4. Then RD address, we have RD address 2 from here. Then RS1. Alright, we have instantiated our register file. So another thing that I forgot to put here is the output instruction bus. So now we got our register file. Now we have to instantiate our instruction ROM. Let's see. Opcode and control word. 15, 15, 14, 13, 12. So we are going to declare a wire here called intermediate control word. That's because we have to apply our invalidation logic. So let's assign our control word output equals validate 18 hex 0 or intermediate control word. So basically, when the invalidate input is 1, the output will be forced to be 0. If not, the output will be intermediate control word, which is the output of the instruction ROM here. Now let's see. Instruction bus out. This one is easy to make. So we got our instruction bus out. Another thing that we could implement to our CPU is a basic system for instruction cache. So we can also make the first implementation of the BatPu2 with cache. So let's see. Okay, we got nothing else to complete. So this is our decode stage. So we can mark this as done, done. Now we have to make our execute stage, which is the hardest part. So let's create a module called xstage.sb. So our inputs are going to be clock enable, okay, clock enable, then the data from our register sources, then our control word, then our instruction bus. Now for the outputs, we have to make output. Let's check one of the most important things we have to implement here. So these parts are going to be for the write back stage, including the clock hold instruction. So how many lines were these? 1, 2, 3, 4, 5. Right. Now we have to also output an instruction bus, so the write back stage can use it. We also have to output our LEU result, which will be used as the calculated effective address or normal LEU result for the normal LEU instructions. Another thing we have to output is memory request, memory write enable, and okay, another thing here, to memory. So let's start our pipeline of our execute stage from the pipeline. So we have to make the buffers for the inputs. RS1 buffer, RS2 buffer. Oh, another important thing we have to implement is register write enable, and here so we have to also include our forwarding logic. That's something extremely important. So we have RS1 buffer and RS2 buffer. So now how to make our buffer for our control lines. And a buffer for our instruction bus. So let's start by making the logic for the buffering. Always ff at posage clock begin. If clock enable begin RS1 buffer is set to rs1, rs2 buffer is set to rs2. Let's see. Oh, here. Control word set to control word in instreg is set to instruction bus. So basically, after we've buffered the input data, the decode stage will be able to decode other instructions while we are executing instructions from the execute stage. So basically, we are allowing parallelism between stages in the pipeline. Using pipelines will allow us to run this CPU at higher clock speeds, and also, well, that's all. We can run it at higher clock speeds by dividing operations. You should check out Mattbatwing's, know which video, but it's in his CPU series. He talks about, I think it was the program counter episode, I don't remember very well. So, we got our buffering system. Now, we have to instantiate our modules. Let's start with the LU. Sorry. LU. Then let's check the inputs. A is going to be, now we are going to create a wire called intermediate rs1, and that will be equals to, and now here we are going to make our forwarding logic. So to make this easier, even though we can use ternaries, we are going to use always comb blocks. Always comb begin. If rd address is equals to instreg 11 and 8, 9, 10, 11, yes, this one. And begin. If rd address is equals to 0, then intermediate rs1 is going to be equals to 0. Else, okay, something that I also forgot. This, and if writing is enabled. Else, intermediate rs1 is going to be equals to writing, and else intermediate rs1 is going to be equals to rs1 buffer. We are going to call this block rs1 forwarding. I forgot about this extra comma. So now we have to repeat that, but for intermediate RS2. This one is 7 down to 4. So, okay, we got our forwarding logic. Now we have to make a wire for the B input of the LU and the immediates. So, to simplify everything, we could split the wires, give them names from. I'm referring to the control word wire. So let's check our instruction run. We are going to pay attention to the execute lines. Up to here, 13 lines. So let's see. Wire 2 down to 0. Control LU up equals control word 2 down to 0. Wanna use tabs directly. Okay, now for the B selection, wire control LU B cell equals control word 3. Wire control cell equals control word 4. Wire control flags update equals control word 5. Wire control jump equals control word 6. Wire control branch equals control word 7. Let's see. Wire control call stack execute equals control word 8. Wire control cstack type equals control word 9. Wire PC in equals control word 10. Oh, another thing that I forgot was making a jump pin, and also a 2PC wire. Let's see. Now, let's see. Memory request and memory write. Okay. 11 wire control mem write enable equals control word 12. So these are our control lines. Let's make comments just in case. Okay, now let's assign the rest. Assign control word to write back equals control word 17 down to 13. Line 27. Oh, here I forgot to place a semicolon. 61. Oh, here too. Okay, now let's continue. So we have to make wire code immediate. Equals. Okay, let's do that later. Now we also have to make a wire code LUB. That one will be equals to control word LUB cell immediate or intermediate RS2. Now here equals control immediate select instruction bus 3 down to 0 or instruction bus 7 down to 0. But look, there's a problem. We haven't made design extension yet. So let's do that now. So we are going to make a concatenation. Instruction bus 3 design. And we extend it 4 times. Set C. A is going to be RS1 buffer. Just in case, I'm going to check something here. Alright. Then B is going to be LUB. Then what is we got? OP is equals to control LUOP. And then just res. We are going to directly connect it to LU res. So have used these things. See what else we have to make. We assign this, also this, not this yet. So let's see. Assign to memory equals intermediate rs2. Let's see what other things we have. Memory request, memory write enable, and jump. We also have to make our flags and branching logic. So let's see. We have to instantiate the call stack. Clock enable execute mode. Let's start with those. Oh, another important thing that I forgot. Input program counter in. And we have to make a buffer for that. Let's see. Now I'm going to join another Discord voice chat. This one, in this case, in the Redstone army, because no one is at the LTDS server, sadly. Let's see. I'm going to join the programmers only voice chat. Alright. I'm going to share my screen. So back. We have instantiated our LU. Now we have to instantiate the call stack. Let's start with the basic parts. Clock is clock. Clock enable is clock enable. Execute is control. Hello.
Hi. Yo, I wanted to say to you, I'm working on a millennium problem, and I think I can solve it using redstone.
Alright, I'm terrible at
I
Redstone, by the
wanted,
way.
I wanted a review.
Hmm?
I wanted a review if you think it's solvable. You know that with redstone you can write in binary code.
Yes.
So, the problem is that uh, you have to find a calculator that finds how you get a result.
Uh-huh.
It's a little strange to say, but you have to find what you need to get a result. So you have to find all the infinite ways to find it. Do you think it is solvable with redstone?
I don't know. I don't know.
You don't know.
I I'm I don't know how to use Redstone. I never used it. I I program on System Verilog, a hardware description language.
But then, do you think it's solvable using, I don't know, Python or C++?
Probably, maybe C. Probably with the C language or C++ or Python, any language, but I don't know if that's possible with Redstone.
Well, I think so, because Redstone is built in a way that you can pretty much solve everything, because it's built like the base form of a computer.
Yeah, but the problem is number one,
Well,
Redstone is slow, and number two, and your main computer is going to crash before the execution finishes.
that's also correct.
So right now,
I guess it's
hmm?
I guess it's simpler to use Python or C++ to solve it. But I'm not really good at programming.
Me neither, by the way. I'm only good at hardware.
Fine.
So right now, I'm making live streaming to YouTube. I'm making the first
Oh,
pipeline implementation of,
What's your, what's your YouTube channel?
and it's the same name as my username, Slickudis.
Fine. I'm going to search you. I think one sec. You here in this career called Steel Kudis. Where are you from?
I'm Argentinian.
Really? Are you Argentinian?
Yep,
I'm trying learning Spanish, actually. I'm from Italy.
nice.
I'm Italo Brazilian.
Spanish may sound hard, but because you are Italian, it's going to be easy.
I found you.
Nice.
Broski, now you got 819 subscribers. You found a new one here in Red's Army.
So it's a funny story how I got those subscribers. So I was bored. It was night. And I remembered about a Pixar movie called Planes. So I remembered a part about World War II. So I made an edit about it just for fun because I was bored. I posted it, and it got 400k views randomly.
GG's, I guess.
I don't know how to react to that, but I, I didn't know I
I
would
think
get.
you're a pro dude. Actually, in Italy now is 23 and 17, so I think I'm going to sleep now.
All right.
It's because tomorrow I have to go to school.
Oh, oh yeah, school. I for,
Because
tomorrow,
today is how do you say it in English? I
uh,
don't remember.
today is Sunday,
Yeah, Sunday. Today is Sunday. In Italian, you would say Domenica. Try to say that.
Dominica,
Domenica.
Dominica. Here in
Well,
Spanish
it's
we
something like
say
that.
we say Domingo.
I know that you say Domingo. Yo hablo un poco de español.
Buenísimo. Ouch, my leg.
Yo tengo que hacer las lecciones de española en la escuela.
And I wish you a ton of luck.
You wish me good luck.
Yes.
Bye. I'm going to sleep.
Goodbye.
Goodbye.
So let's continue. We have to make our data out. We have to connect our data out. So data out is going to be connected with, we're going to make another wire called cstack and top, cstack top. And now here, now we can assign our output to the program counter. Assign to PC equals control PC incel cstack top and instreg 9 down to 0. Oh, another thing I forgot was making the mode, adding the mode connection. Mode equals control cstack type, comma. So now let's see. Memory request, memory write. These ones are easy. Let's assign them here. Equals control word no wait, equals control mrec and clock enable. So basically we have to use clock enable too, and that's because so when the clock is disabled we don't output control signals to memory, so any external peripheral can use them. Now assign memory write enable equals control mem we and clock enable. Let's see, we have already assigned that. Okay, we have to make our flags now. So I completely forgot about that. So now we have to make another output here. Output 0, output carry. So this is going to be easy. Okay, not so easy. The easiest one is the 0 flag. Assign 0 equals and we have to make a NOR reduction res. So here we performed a NOR reduction. Because you know, if any bit is 1 and we make an OR reduction, the output will be 1 because it's an OR. Hello. So back to the live stream. So we perform a NOR reduction, and with that we can get if the result was 0 or not 0. Now for carry, this is going to be much harder. We have to make a logic called carry out.
That's my computer account right there. Technically, I'm a coder, like slightly.
Nice.
So yeah, because I can code a tiny bit of HTML.
I'm on a live stream right now. You can say hi if you want to.
Let me watch on my computer. Let me
Right.
watch your
So
screen share.
right now I'm live streaming on YouTube plus on Discord and making the first pipeline implementation of Mattbatwing's BatPu2.
I know like the smallest bit of HTML, so I'm not the best at coding, obviously.
Uh-huh.
But didn't I show you the thing I built with the thing I did with HTML where I made it show the time?
Wait, give me a second. So we have
I think I showed it to you.
to prevent problems related to bit widths, we are going to use more concatenations. We are 0 extending A from 8 to 9 bits. The 9th bit is going to be our carryout. System Verilog works differently from any other type of logic system, so we have to extend this part. Now here we have to concatenate 7 down to 0 and same here. And now always comp begin case OP end case. Okay, we can make this easier.
Why does it every single time I try to open Opera GX, it keeps trying to download AnyDesk over and over again?
I don't trust Opera. You should have seen their history.
I'm not sure about their history, but I just use it because because everyone that I know, everyone that's my friend uses Opera GX, and it's kind of my style because I get to mod and all that.
Yeah, but the company Opera is known for stealing data. It's a Chinese company. So if your friends use it, that doesn't mean you should use it. It's like the famous phrase that a parent says, "If would you jump off a bridge if your friends did?"
I know that's what parents always say, bruh. It's an old line. That's what they always say.
But they always end up being right, isn't it?
Most websites I never sign into, so they probably won't even. Or so the websites that I do sign into, they're not very important at all. They don't have any of my information on them or anything.
So let's see. If there's a NOR reduction, if the NOR reduction ends up in true, basically all operations except addition and subtraction, then carryout is going to be 0, else it's going to be the highest bit of add sub. Carryout. Now we have made our carryout logic. Can't find the definition of variable op. Here, now I fixed it. So we have made carry out 0 if not add or subtract. So we have made our flags logic for the ALU, and now we have to make our flags register. So we have to go back to the execute stage. So we are going to add the new inputs 0 and carry. So let's make two wires, wire LU 0, wire LU carry. So we have our flags logic. Now for the next step, how to make our flags register. So make reg 10 flags equals 0 as the initial value. And now we make an always flip-flop block. Always ff at postage clk begin if clock enable and control flags update, then flags is set to carry comma 0 in a concatenation end. We call this block update flag. Okay, so we got our flags now. So we have made our flags. Now we have to make our conditions. Before that, I'm gonna check something quick. I'm going to search for some music, some classic Mozart. So let's see. I'm going to copy this link. So right, back. Now we have to make our conditional jumping, so we are going to use XOR logic. So let's check the conditions. Not equals 0 equals 1, not equals 0 equals 0, greater than or equals carry equals 1, and less than carry equals 0. So first we have to make a wire called branch, and this wire is going to be equals to instruction bus bit 8, 9, 10, 11. So you got LU carry, LU 0, and now next this. And we make an XOR inversion. Inst bus 10. So right here we got our branching flags logic. We put a multiplexer between LU and carry and then placed an XOR gate. Now our next step is assigning the jump output. Assign jump equals control jump or control branch and branch. I'm gonna call this branch branch out. Okay, no, just branch. So we have made our branching logic. Let's see other things. Signal definition not found, line 33. Okay, syntax error, classic one. Let's check the stream chat. Curious if... Okay, no one is here. But maybe one day I will have people interested in this, but not yet. Destination doesn't want me to do that yet. Let's check for other syntax errors. Can't find definition of variable carry, can't find definition of variable 0. Where is that? Let's check the LU. Okay, I'm removing the logic part here, I don't need that. Line 72. Oh, LU carry, LU 0. Then these ones, I forgot about that. Instruction out. Assign inst out equals inst reg. Line 35. Huh? Oh, inst bus out. What does it mean by... Oh, intermediate RS1, alright. Signal not used, flags. Oh, yeah. I understand what's happening here. Flags 1. flags 0. Alright, no more errors. We have made our execute stage. So we're going to take this as done. Done. And we have to make our right back stage now. Another thing we have to add here is the top level of the core, and maybe a basic instruction cache. So for our instruction cache we could use 4 words per instruction. No, we could use 8 by 8, 8 lines, 8 lines, each one of 8 instructions, basically 8 times 16. We could get 128 bytes of instruction cache. That would be perfect because our instruction ROM is 1 kilobyte, has 1 kilobytes of memory of data. Alright. So it's here. Oh hello, greetings. So let's see, we have to make the right backstage the top level of the core and the instruction cache. So let's check. Okay, back to work. Have module, right back, stage. Okay, what's that noise that I'm hearing from Discord? I'm gonna lower Diamond's volume by a little bit. Okay, so back to work. Right back stage. So our inputs are going to be input clock enable, input 7 0 from LU for memory. You also have to put the control lines. Input, first you need the instruction bus. Input inst bus, and input yes, so I don't get errors that I don't like. Now input 4.0 control word in, and for the output 3.0 rd address output to reg data that is going to be sent to the registers, and output reg write enable. So the write back stage is the easiest stage. We first have to make our buffers. Reg 7 0 lu buffer equals 0. Reg 7 0. We don't need a memory buffer because, like in the instruction memory, block RAMs have their own output buffer, so we don't need a buffer for memory. Now we have to make a buffer for our control lines. Now wait, a buffer for the instructions. Inst reg. Then, now for the control lines. Now we have to make our always flip-flop block. Always ff at postsearch clk begin if clock enable begin lu buffer set to from lu inst reg is set to inst bus and control word set to control word in and okay. Now we have to make our always com block for the resistors. So we declare this output as a logic. Oh, before that we can do the easy part. Assign reg write enable equals control word. Oh, by the way, I forgot. Clock hold. Let's see. Reg right. R diesel. Okay, clock hold. 0 1 2 0 1 2 3 4. Ah yeah, 5 bits. I forgot about that. Now, the reason we are halting the clock, in the case of using halt, because the reason we are using the write back stage is to prevent data hazards. Because if we start the clock from the decode stage, the CPU won't have time to write, for example, to write to a register that was to use a writing instruction from the write back instruction. For example, we have to first finish all the instructions and then halt the clock. Now Alright. So the kid left. Okay. Back to work. Okay, we should also make a hazard prevention system in the top level in case of memory writing. We will see that later. Um, now, I'm going to make this a logic 2. Now let's make the multiplexer. Always comb, begin, select, dest, end. Okay, now let's case, control word, to 1, and case. Section 0 is gonna be for A, rs1 basically. So rd address equals inst reg 8, 9, 10, 11, okay. This one is for B. Seven and 4. 3, 0. Default rd address equals 0. Okay, let's make comments just in case. A, B, C. Now let's assign our output. Assigned to reg equals control word 3 lu and memory. Error at line 17, let's see. Expected identifier. Unexpected identifier. Expecting. Alright. Line 17. Okay, let's use the test bench checker just for that, so we can exactly find the error. Hmm. Okay, my bad here. Okay, now it's fixed. Now syntax errors. So this is our live stream for today. We'll probably continue tomorrow on streaming. It was a nice, or maybe in an hour, I don't know. But it was a nice time to be with you guys. If anyone was watching this, um, so let's complete this part. Done. So we only have to make the top level and the extraction cache. So that's all. And see you in the next episode, guys.